Hi, okay, I am going to walk you through how I elucidate the structure of this molecule with molecular formula C10H12O using these combined spectra. And this is group 9 for the week 15 activity. So the first thing I want to do is calculate the degrees of unsaturation. So I do that down here by looking at, here's the equation that I use, but I'll talk it through here. So typically, the equation for this would be, you'd say 2 times the number of carbon molecules plus 2 hydrogens. So normally without any unsaturation, this molecule would have 22 hydrogen atoms. So 22 minus 12, which is how many it actually has, is 10. And 10 divided by 2 gives us 5 degrees of unsaturation. So off the bat, we know that this molecule might have 5 double bonds or 5 rings, or maybe a benzene ring and 1 double bond. Benzene ring accounting for 4 degrees of unsaturation. So I'll switch over to this to walk through the different spectra. So this is the infrared spectroscopy results. And this is good for identifying functional groups in our molecule. So here, the important ones that I've identified are this peak here at about 1700, this strong peak, which signifies the C double bond O stretch of a carbonyl group. These two here at 1600 and 1550 represent the C double bond C stretch of an aromatic. So I have this is cheating a little bit. This shows the molecule I'm thinking it is, but I'll point out, so the C double O stretch would be this bond here. The C double bond C stretch are these 3 within the benzene ring. And then this peak here at 3000 is the CH stretch. And I have multiple peaks, so these ones here are from the benzene ring, which would be each of these individual hydrogen atoms coming off of it, and then the main peak down here would be from the isopropyl groups down here. Cool. So from the IR spectra, I know that there's a carbonyl, an aromatic, and then the CH stretches. So as we guessed with the degrees of unsaturation, an aromatic and a carbonyl will account for those 5. Moving on to the carbon-13 NMR spectra. This, let's see, the main peaks we have here, the one that jumps out first is this one furthest downfield at 190, which is typical of a C double bond O or carbonyl group. We then have at 160 right here. This is the C on the C to C double bond O stretch. So that is likely this C right here on the molecule. Just upfield from that at 135, we have this C on the other side of the molecule, this one here, which is then bonded to this carbon and the 2 methyl groups. At 130, we have these 2 equivalent carbons on this side and this side. And at 125, we have these 2 equivalent carbons here. Let's see. And then finally, this one right here shows up, the peak at 35, this one here. And then the 2 methyl groups will be equivalent peaks, and the furthest upfield at 25. Cool. Okay, moving on to the H1 NMR spectroscopy. Again, I'm going to start here on the downfield side, and we see a chemical shift at about 10, which is common for aldehydic protons, this one out here. And we can confirm that it has an integration of 1, which makes sense. There's no other neighboring protons next to this. It's just the one proton here, and then its multiplicity is a singlet, showing that there's no neighboring protons. And then again, that chemical shift of 10 is common for aldehydic protons. The next one, this doublet here at 7.9, both of these in this range are common for aromatic protons. And so if we look at the integration values first, we can see that there's 2 equal or equivalent protons for each of these peaks, which makes sense with our benzene ring that has a plane of symmetry in it. So these 2 that are more shielded or further downfield at 7.9, sorry about my dog barking in the background, represent the hydrogens coming off of these 2 carbons here that are closer to the carbonyl and being partly shielded by that carbonyl. And we can confirm that with their multiplicity, which shows that they're a doublet, meaning they have 1 neighboring proton, which is from this carbon down here and this carbon down here. So similarly, the next peak here at 7.4 is these 2, which has the same morphology. It's a 2H integration, meaning there's 2 equivalent protons, 1 and 2, and it's a doublet, meaning it has 1 neighboring proton, which is the 2 that we just talked about. And then the last 2 peaks, this one at with a shift of 3 has a 1H integration, meaning it's just a sole proton all by itself in that location. There's no equivalence, and it's a septet, meaning it has 6 neighboring protons. And this one is really diagnostic and helpful because to have 6 neighboring protons means it's likely an isopropyl group with 2 methyls attached to it. So we feel good about assigning that peak to this carbon and hydrogen right here, or the hydrogen on that carbon. And then the final peak down here at 1.1 about has an integration of 6H, which again is diagnostic of two equivalent methyl groups. And we'll confirm that by looking at its multiplicity, which is a doublet. It has 2 peaks, meaning that these 6 equivalent protons have 1 neighboring proton, which is the one right there. So putting all 3 of these together, we can feel confident about this structure, which is a benzene ring with a 1,4 conformation of the 1 being an aldehyde functional group here, and on the 4 position we have an isopropyl group. And this molecule its common name is cuminaldehyde, which is responsible for the scent in spiced cumin. Cool. All right, so that's it. Thanks for listening.